This video is going to cover what we call the fundamental theorem of algebra. It sounds like a really big concept, but really it's not as big as it sounds. You actually already know most of what you need to know for the fundamental theorem of algebra. The only thing that we're going to get into today that's a little bit new or different would be the imaginaries. And so we'll discuss that along the way as well. Okay, so the main idea of the fundamental theorem of algebra is that when you're solving an nth degree polynomial equation, there will be exactly n solutions or n roots to the problem. You already know that. That is what we've been talking about for a couple of days now. Now, the new part is that n includes the rational and irrational solutions, complex solutions, and repeated solutions, which is also called multiplicity. Let's take a look at an example. This is a fourth power. That means it must have 4 solutions. Those 4 solutions include all of those other things that I just said: rational, irrational, complex, and repeated. And if you're not sure what those mean, then you might take a minute to write out in the margin what those mean. And so out here in the margin, I have defined these if you're not sure what they mean. Rational are integer and fractions. Irrational, typically in our world, that's going to mean square roots. It's just any decimal that doesn't repeat and doesn't stop. And that typically, when what we're doing, that's going to be square roots or cube roots, things like that aren't perfect. Complex numbers, you know that already, that is your i's. And then when I say multiplicity or repeated solutions, that means if you have x squared, that counts as 2 solutions. Or x to the third counts as 3, etc. Okay, so but again, the main idea of the fundamental theorem of algebra is if there's an nth degree, there are n solutions. Then we have something called the complex conjugate root theorem. We talked about complex conjugates before when we had them in the denominator and we had to multiply to get them out of the denominator. And so complex conjugates root theorem says if a plus bi is a root of the polynomial equation with a real number coefficients, then its conjugate, which is a minus bi, is also a root. So again, remember that a plus bi, a minus bi, you remember that from the denominator when we were doing imaginary numbers. This theorem matches up very closely with a theorem we had just the other day, which said basically if 2 plus square root of 5 is a solution, then so is 2 minus square root of 5 must also be a solution. So this theorem is very similar to the irrational root theorem. Well, let's take a look at what that means in terms of i's. Well, if 2i is a root, so is negative 2i. And if 3 plus 4i is a root, so is 3 minus 4i. Okay, how about if 8 minus I is a root? What would the conjugate be for that? Well, it would be 8 plus I. So the complex conjugate root theorem, like I said, very similar to the irrational root theorem. All right, well, what does this mean for us? What this means for us is sometimes in the textbook or in tests or quizzes, they're going to throw you these tricky little questions. It says, write a polynomial function in standard form with zeros at x equals 2 and x equals 5i. Okay, I think you already know, I hope you already know, that one of these factors is going to be x minus 2. What are the other factors? Well, one of them must be x minus 5i, for the same reason x minus 2 was. Now, the tricky part is they didn't tell us, but we just learned if 5i is a solution, then negative 5i is also a solution. And so we also have to put in here x plus 5i. Now, we're not done because it says standard form. In other words, we need to multiply this out. My little hint to you would be to multiply the pairs first. And I think we did one of these when we did the irrational roots also, that if you had these two and you had to multiply a couple of them together, it's easier to multiply the pairs first. Because what happens is, because they're conjugates, that's the whole purpose of conjugates, some things are going to drop off. So I'm going to save this x plus 2 until later, x minus 2. I'm going to save that x minus 2 until later. And I'm going to take a second to multiply this out by foiling. Now I have to go back and remember, and again, this is a lot like the denominators we're working on. This is still x minus 2. This is x squared. The plus 5i and the minus 5i drop off. And then here I have negative 25 times I squared. Well, we remember from before that I squared is negative 1. So that must mean plus 25. Notice that's just a binomial. That's why I'm suggesting do your pairs. But that plus 25 is a plus because this was minus, but that's negative 1, so that's plus 25. And again, hopefully you remember that from quadratics when we had the complex numbers in the denominators. I'm not done yet because I still need to multiply this out, so I'm going to take a minute to multiply that out. So I multiplied this out, and just the order I had mine written in, it ended up kind of being out of order over here. So I went ahead and put things in the right order. Because it does say standard form, I need to have it in the correct order. X to the third minus 2x squared plus 25x minus 50. That is my final answer. So basically on that section, the main idea is don't forget the conjugate. So if they have a 5i, you have to have a negative 5i. Whatever they have here, make sure you have the negative with it as well, and then you just have to multiply it out and get your final answer. Okay, the next section says to find all roots of this polynomial. And I am looking at this and I'm thinking x to the fourth, but it's a trinomial, and then I have x squared in the middle. I'm going to use my u method, where I'm going to let u equal x squared, and I'm going to let u squared equal x to the fourth. And so what I have here is u squared plus 5u minus 36. That I can factor. I'm going to take a second to factor that. So I factor that. It is u plus 9, u minus 4, because 9 times negative 4 is negative 36, and 9 minus 4 is 5. Now I need to plug my x's back in. All right, I plug my x's back in, and I get x squared plus 9. Over here I get x squared minus 4, but that does factor down to x plus 2, x minus 2. Now, I'm not done because it says to find all the roots. I just factored it, which I need to do, but now I'm supposed to set each of those equal to 0 by the zero product property. Okay, these two were really easy. I just had to subtract 2, add 2. I get the answers of positive 2 and negative 2. Those are my real solutions. However, I also have this one over here. This is going to generate a couple more solutions because, remember, this was a quartic, a fourth degree, x to the fourth. If it is a fourth degree, it's supposed to have 4 solutions. So far, I only have 2. What are my other 2? Well, I need to solve this. So I'm going to subtract 9 and take the square root. And what is the square root of negative 9? It is plus and minus 3i. Now I have all 4 solutions. Because it was x to the fourth, I have to have 4 solutions, and those are my 4 solutions. So again, the main idea here is you have to solve it. How do we solve it? Well, typically we solve it by factoring. And when you factor it, make sure you find all 4 of them. In this case, we had 2 real solutions and we had 2 imaginary solutions. All right, this next example, it really takes some thought. You really have to think about this. You can't just jump in and it's not a quick problem. It's just not. So we have to look at some things. First of all, find all roots. However, this has 5 terms. I don't know how to factor with 5 terms. The other thing is they tell us that 4i is a root. Well, if 4i is a root, what's the other one? Negative 4i is the other root. So they are giving us some hints. I'm going to figure this out. I'm going to come over. I know I need some space because I've done this. So I need some space. So I'm going to come over the margin. Step 1. I'm going to utilize this hint. If these are my roots, then that must be x minus 4i and x plus 4i. I'm going to take a minute to multiply this out. Okay, I multiply this out, my 4i negative 4i drop off, my negative 16i squared turns into a plus 16. Okay, that is one of my factors. If that is a factor, I can divide it into this polynomial. The reason I couldn't do that before, I don't know how to do division with imaginary numbers, do you? I don't know how to do that. So I had to multiply it out so I get some real numbers so I can do my division. That's one thing. Another thing is, remember that this is really x squared plus 0x plus 16. The unfortunate part of that is not a binomial. It's not a linear term. It's not a binomial. In other words, I have to do long division, not just synthetic division. So my step 2 is going to be to set up a long division problem with these polynomials. Okay, so I'm going to set up my division. Remember, this polynomial goes under the division sign. The trinomial that I'm trying to put into it goes outside here. So I set it up that way. To start my long division, I look at the first term and the first term, and I think about x to the fourth divided by x squared. What is that? That is x squared. Another way to think about it is x squared times what would give me x to the fourth, and that's x squared. Next step in long division is to multiply this out by distributing. All right, I multiplied out by distributing. That gives me x to the fourth plus 0x to the third plus 16x. I'm supposed to subtract. And I'm put parentheses there to remind myself I'm subtracting all of this. So that first thing drops off. The next one is just a negative x to the third minus 0. That's negative x to the third. 10 minus negative 16x squared is a negative 6x squared. I need to bring down my minus 16x. Now I start all over again. X squared goes in to negative x to the third how many times? Well, it goes in negative x times. I distribute. I now subtract. Minus negative means plus. And when I do that, this drops off. I might go ahead and call that a 0x. So I distribute and then I subtract. And I have one last turn because x squared goes into negative 6x squared, negative 6 times. So I do that, I get a remainder of 0. Let's think about what are we even doing here. The original question was to find all of the roots. How many are there altogether? There's going to be 4 altogether. I know 2 of them because I had a hint for one of them. I quickly, easily found the second one. So 4i and negative 4i are 2 of them. I need the other 2. So I figured out, okay, if I divide by 4i and negative 4i, then I'm really dividing by x squared plus 16. And when I do that, I get this. So now the question is, what are some factors of this? What are some roots of this? And so step 3 now is going to take that and factor it out, right? Because think about that. If I divide those out and I'm left with this, then what will go in to this? Well, x minus 3 goes in and x plus 2 goes in. And so those two solutions are a positive 3 and a negative 2. So the original question was to find all roots. There should be 4 of them. I have found all 4 solutions. The solutions are x equals 3, x equals negative 2, and x equals positive and negative 4i. Those are the 4 solutions. It wasn't obvious how to jump through all those hoops. So we have to kind of think about it for one, but number 2, we probably have to practice it a little bit. And so Yes, there will be questions like this on the test, but we're going to have some practice so you can train your mind on how am I supposed to do these problems. Let's talk about real versus non-real answers, because on this last problem, there were 2 real answers and 2 imaginary answers. In fact, on the one on the previous page, there were also 2 reals and 2 imaginaries. And so when do we know how many are going to be real, how many are going to be imaginary? Okay, well, let's think about this. A cubic has how many solutions? Well, it has 3 total solutions, right? And sometimes that can look something like this. So I didn't draw it very exaggerated, but there's one, and there's one. That is 3 real solutions. Real solutions are when they actually cross the x-axis. If they cross the x-axis, those are real solutions. And so we had 3 real solutions. We're only supposed to have 3 total. So how many non-reals do we have? Well, we must have 0 because we've got all 3 of them right here. Could there be another situation? Could there be some way to have non-real solutions? Do you remember when we did quadratics last unit that it was like if there was one floating up here, that would be imaginary or non-real answers. That has imaginary solutions. Similar thing with cubics and all the polynomials that we're going to do. That couldn't we draw this like this? And so now, how many real solutions are there? Well, there's only one. It only crosses one time, crosses the x-axis. The other 2, there are 2 more up here, but they're floating up here. We don't know exactly where they are. They are non-real. They're imaginaries. Now, they're answers. It's like a 4i and a negative 4i, but we haven't studied how to graph those. So those are non-reals up there. Would it be possible to have 2 real solutions and 1 non-real solution? Well, think about that. Is there any way you could graph that? 2 reals and 1 non-real. Well, I'm trying to think if I turn it upside down, would that do anything? Well, that just gave me 1 here. Is there any way I could do this where I had 2 reals, and there's not. There is not, just because of the way it is drawn, the way it is configured, you can't possibly have 2 reals and 1 non-real. Let's try to make it, okay, maybe it crosses twice like this. Well, it has to come back down. Okay, it's going to cross twice. Well, it has to go back up. See, that's how a cubic goes. And so it is not possible. It's not possible to have 2 reals and 1 non-real. Another possibility would be maybe it bounces. All right, well, then maybe it bounces, but it still has to come back. And this, although this looks like 1, this one over here looks like just 1, it's actually 2. We call that because that's like an x squared. We call it 2. So those are 2 reals. That makes a total of 3 reals. So no, it is not possible to have 2 reals and 1 non-real. That was for cubics for 3rd degrees. What about for 5th degree or 6th degree or even 4th? We skipped 4th, but that could be a question as well. For a 5th degree, remember that a 5th degree, because it's odd, it also, like a cubic, has 1 down and 1 up. And if we had an x-axis here, we would have 1, 2, 3, 4, 5. What I just drew has 5 real solutions. What if we moved the axis and said, instead of having it there, let's move our axis down here? Well, in that case, it only has 1 real. Now, if it has 1 real, it's supposed to have 5 altogether. If it has 1 real, it must have 4 non-reals. And those in this case are the ones 1, 2, 3, 4. I'm not going to count that one because that one's already coming down here. Basically, they have to add up to 5. The sum is equal to 5. And so if there are 5 reals, there are 0 non-reals. What about 3? Could we do 3 with this? Yes, we could do 3. It could look something like this, where there's 3 of them here. So there could be 3 real. They're supposed to add up to 5, so there's 3 reals. How many non-reals are there? There are 2. Could we have 0 reals? Well, no, because one of these ends is always going up to infinity or down to infinity. So one of those ends is always going to cross no matter how far away it is from the x-axis. See what I mean? So it always has to have at least 1, if it's a 5th degree or if it's a 3rd degree. So again, these have to add up to 5. And in the case of an odd, it has to be odd, odd, odd. Let's talk about 6th degree. Well, think about, what does a 6th degree look like? 6th degree is going to look something like this or something like this. Okay, how many solutions does it have? Typically, we think of it as having 6 reals, and that means it has no non-reals because, again, they have to add up to 6. Well, what could those be? If it was 6, it'd be like that, where they're all 6 of them are going through. Could we have a different combination? Okay, we could have something like this, where only 2 of them go through. And if there's 2 reals, there must be 4 non-reals. Now, the other thing about the non-reals that we didn't talk about yet is that the non-reals have to come in pairs. Remember, non-reals means imaginaries. And we just talked about, if we have an I, we must have a negative I. And so they have to come in pairs. So 0, 2, or 4. Okay, same thing over here. They have to come in pairs. And so if they're coming in pairs, 0, 2, 4, or 6. And then their sum has to be 6, so this must be 0 and this must be 4. Could it have 0 solutions, 0 real solutions? Sure, it would just be like a parabola that was like floating out there. Okay, so that's possible. So the idea in this section is that 2 things. First of all, the total number has to add up to the degree. Secondly, the non-reals have to come in pairs. So those are both things to know and to remember about. Okay, again, we'll work on some of this tomorrow in class, and we'll have plenty of practice before the test comes next week.